All right, so let's talk about radicals. And the first thing we're going to talk about is, I don't even know if you know what the term radical means. You do. You've been working with them for a while. It's just a fancy name for your square root sign. That's what a radical is. Okay, so a radical is basically just your square root sign. So we're going to start by writing these numbers somewhere, because they are going to become your best friends. We're going to write these numbers over here. 25. You could probably come up with them on your own at this point, right? 36, 49, I always skip that one, 64, 81, 100. Does anybody know what 11 squared is? Good. 144. And usually that's like about where you stop, but because you only had to learn up to your 12s. Does anybody know what 13 squared is? I want you to... Yep, just think of the multiples of 3 are 6, 9, 14 squared, switch those around, and 15 squared, 225, awesome. Okay, so these are called our perfect squares. They are called square numbers. These are the first 15. 1 times 1, 2 times 2, 3 times 3, 4 squared, 5 squared, 6 squared, okay? These numbers need to be in your head because you're going to rely on them a lot, all right? So you know that when you see one of these numbers under that sign, that you know that you just find the square root of it. That's what it's called. Okay, we're going to talk about having positive and negative square roots, because what you realize is that whenever I ask somebody what's the square root of 16, everybody almost 100% of the time will say 4. And that's right, that's one of them, but what's the other one? Negative 4, okay? So every number has a positive and a negative square root. However, when we deal with square roots, we are mostly dealing with the positive one, and that's called the principal square root. So most of the time, that's what we want, right? So if I were to say to you, give me this, that negative sign also means the opposite of, we know, right? So you would read this. What is the opposite of the square root of 36? So I know what you're thinking. Well, if the square root of 36 could be a positive or negative, couldn't this answer be a positive or negative? Okay, they want you to take the principal square root, the positive one. So if the square root of 36 is 6, and they want the opposite of it, your answer is a negative 6. Okay, so that negative just kind of hops over to your answer there. Okay, what's the square root of 1? A positive or a negative 1. What's the square root of 0? Just 0. Okay, those are just two I wanted to make sure you knew, because everybody gets a little confused. Okay, now we're getting into the good stuff. If I were to say to you, hey, what's 3 times 5? You would say 15, right? So what we're going to talk about today is what is the square root of 3 times the square root of 5. And what do you think it would be? The square root of 15. And you would be absolutely right. Okay? To kind of show you what I mean by this. And before I gave you this answer right here, you may have been tempted to take a calculator and find the square root of 3. Does everybody know how to find the square root on their calculator? It's the blue button above the x squared button. And to activate it, you hit the second key. So the square root of 3, if your float was set to 2, you would tell me is 1.73. Then you would take the square root of 5. This is probably how you would do this problem, which is 2.24. And then you would take the 2.24 and multiply it by the 1.73, and you would get 3.87. And that would be your answer, and you would be right. But what do you think the square root of 15 is? It is. It's 3.87. So if the square root of 3 is this and the square root of 5 is this, all I'm doing is taking the square roots and putting them in their decimal form. That's all we're doing. Well, not all. So for this problem. So what I'm saying is, instead of dealing with all this, is this an acceptable answer? Heck yeah. And as a matter of fact, that's how I want my answers. I want my answers with the radical in it today. No more decimals. No more estimating like we did before. I want you to put your answer as that. Okay? So we have radicals in our answers today, which means, by the way, if I did this, do you think I'd get the same answer instead of each of them being separate? If I put them both under one radical? Yeah, I would still get my same answer. So real quick, nope, don't want to do that yet. What is the square root of 7 times the square root of 2? It's the square root of 14, and that's all there is to that one. Okay? What is the square root of 6 times the square root of 6? Nope. You have to be very careful. All I heard was 36. The square root of 36. Okay? Because the square root of 6, okay. The square root of 6 is 2.45. And 2.45 times 2.45 is 6, not 36. You have to be very careful. So, but what's different about 36 than 14 was and 15 was? It's a perfect square, Amber says. Yes. So you know what? And here's kind of where I start silly analogies, but it helps. Pretend like this little radical sign is like a prison or a jail, and if you're special, you get to break out of it. So these are special numbers, right? So this special number 36 is free. Okay? But that's not special. It's 14. There's nothing special about 14. It's not a perfect square. It's got to stay under that radical. Yes?
So what's the answer?
The answer for the square root of 6 times the square root of 6 is 6. So what do you think the square root of 10 times the square root of 10 would be? Which is 10. So the square root of 10 times the square root of 10 is 10. And here's why. You got that little step in between that makes you multiply them, but then you turn around and take the square root of it. So what do you think the square root of A times the square root of A is? A. That's it. Okay? All right. Now, if I were to say, what do you think the square root of 9 times 4 is? You would multiply 9 times 4, right? Because that's what your first instinct would be to do. You would get 36. You would recognize 36 as one of those special cases, and you would tell me the answer is 6, and you would be right. But I want to show you that there is an option of doing it a different way. See here, I had them separate and in their own separate radical, or I chose to put them in the same radical. You have that option. So could I take the 9 and the 4 and separate them? And what is the square root of 9? And what's the square root of 4? And what's 3 times 2? 6. So it works whether they're separate or together. This will come in handy for when I ask you to find the square root of 81 times 49. If you want to multiply 81 times 49 and then find the square root of that big number, you go right ahead. But for me, I'm going to separate them, find the square root of them separately, then multiply those square roots. The square root of 81 is, and the square root of 49 is, so the answer to this is 63. If I would have chosen to just do it in my calculator, 81 times 49 gives me 3969, and then if I were to take the square root of that, I'd still get 63, right? But wasn't this way a little easier to kind of break it down? Okay, so you have to know that there's all kinds of fancy little tricks and rules that you can use when you're simplifying radicals, and that's one of them. Another one is when you have the same number under the radical, your answer is just that number, right? Because it's kind of like, why would you square it just to turn around and unsquare it? Okay? So keeping that in mind. All right, so moving on. This is where it started to get a little tricky. Okay? So, if I ask you, first of all, before we're going to simplify radicals just like you simplified fractions, right? If I gave you the fraction 4/10 and asked you, first of all, is it in simplest form? You would say no. Because you know that, and how do you know that it's not in simplest form? Yeah, because Ethan says both of them can be divided by 2. So it has a GCF other than 1, right? So I could divide each by 2, and I would get 2/5. And now, is it in simplified form? Yeah, because its GCF is 1, right? Are there times where maybe you did 24 over 30, let's say 36, and maybe you did divided by 2? So for some kids who have a hard time with their multiplication facts, I'll say just chop it in half. So 12 18s. Then can it be chopped in half again? Yes, divided by 2, 6 9ths. Then it can't be chopped in half, but can it be chopped into thirds? So eventually we get them to this answer. But wouldn't it have been a whole lot easier if I just divided by 12? Yes. And you know that, and your brain is able to think that way. So now, let's kind of make this transition over to radicals. I'm going to give you a radical and ask you if it's reduced, if it's in simplest form. Well, you know that's not, because it's one of those magic numbers. Now it's in simplest form, right? Okay, 25. Is that in simplest form? No, because the square root of it is 5. Now, wait a second, and if I give you that or that and ask you, are those in simplest form? I will tell you right now that one of them is and can stay that way, and one of them isn't. Which one do you think is, which one do you think isn't? It would be a total just educated guess right now, because right now you don't know where I'm going with this. Nasser? Okay, well, opposite. You have the opposite. You would think that 10, first thing I need you to do is get out of your mind like the idea of doing halves, okay? As soon as I show you this little thing over here, you're going to kind of get it. Do you remember back in, 4th grade when you did those little prime factorization trees? Those were so fun, weren't they? So if I took the prime factorization of 12, you know the prime numbers are like 2, 3, 5, only numbers that have one factor in itself. So I would take and say 12 is 2 times 6, and then I circled it because that branch was done growing, remember? Then I could break 6 down into what? 2 times 3, and then those are both primes. So the prime factorization of 12 is 2 times 2 times 3, and if the teachers got really fancy, they let you write it with an exponent, right? Those were the days, okay? So we're going to kind of use a concept similar to prime factorization to simplify radicals. Now the first thing is, how do I know if it needs to be simplified or not? Because looking at both of these, I don't know. Well, let's look at the factors of 10. The factors of 10 are 1 and 10 and 2 and 5. What are the factors of 12? 1 and 12, 2 and 6, and 3 and 4. Whoa. What's so special about 4? Dun, dun, dun. It's one of those numbers on our list. Didn't I say that these numbers are going to be like, you are going to need to know those. So 4 is a factor of 12, and it just so happens to also be a perfect square. So watch. Your goal, if you pretend like this is a video game or something, is to free as many of those poor, tortured numbers from those radical signs as possible. So if I were to break 12 down into the square root of 2 times the square root of 6, I would fail that level. Because neither one of those are coming out, right? Because neither one of those are perfect squares. So to break 12 down, what's a better choice? Yes, the square root of 3 times the square root of 4. And it doesn't matter where you put it, right? So watch what I do. 4 is a perfect square because it's one of those magic numbers on that list. I pull the 2 out of it. And whatever you manage to set free goes first. And then whatever's left in the radical stays at the end. So guess what another way of writing 12 is? 2 times the square root of 3. Let me just show you that the square root of 12 is 3.46. And 2 times the square root of 3 is also 3.46. Because that's another way of writing 12. You're going to be given it this way. I want you to turn it into this way. Yes, Nasser. So what do you do with 10? You leave it. It's kind of like saying, reduce that. And you would say, I can't. That's as simple as it's going to get. 10 is as simple as it's going to get. Okay? So if I ask you to reduce, let's say, the square root of 20. 2 and 10 do me no good. But what else works? Okay? The square root of 4 times the square root of 5, which means then the square root of 4 is 2. And once you find the square root of it, that radical sign is gone, right? And what's left over? 5. So another way to write the square root of 20 is 2 square root of 5. How about that? You seeing it? What's that? Yes, let's do some more. So square root of 18. Yeah, 3 and 6 are good, but they don't work because neither one of them are perfect squares. But what is 9 and 2? So the square root of 9 times the square root of 2. And the square root of 9 is 3. So it gets pulled out. And what's left? 2. So another way to write the square root of 18 is 3 square root of 2, right? Okay. So let's talk about how do you know if it's simplified or not. So we're gonna make 2 little columns. Simplified and not simplified. And if it's simplified, that means that it has to stay under the radical. It can never come out. And if it's not simplified, it means you need to start breaking it down and pulling some things out. Perfect squares. So, I feel like as soon as we make this list, it'll get clear to you. So, the square root of 1 will stay. The square root of, the square root of 1 comes out. The square root of 2 has to stay under the radical because it's not a perfect square, right? The square root of 3 stays under the radical because it's not a perfect square. What column does the square root of 4 belong in? Obviously not, because the square root of 4 comes out and it's 2. The square root of 5 has to stay because it's not a perfect square. Okay, now stop for a second. The square root of 6 stays under? Yeah, because the factors of 6 are 1 times 6 and 2 times 3. And are any of those perfect squares? Nope. So keep going. The square root of 7, that has to stay. Now, what I'm about to write next may confuse you. The square root of 8 doesn't belong over there. Why does the square root of 8 not belong on the not simplified side? Good, because 8 has a factor that is a perfect square. 8 can be broken down into the square root of 4 times the square root of 2, right? And what is the square root of 4? 2. And then this 2 stays left over. Got it? How about 9? Well, that's a perfect square. That's like a bonus. That's where it's a given. That comes out because it's 3. This is where you start to probably think, what? 10 is simplified? Yep. 1, 10, 2, and 5, none are perfect squares. It's got to stay in there. Square root of 11 stays. Where do you think the square root of 12 goes? On the not simplified. Because the square root of 12 has a factor that is a perfect square. And it's 4 and 2, right? So this is going to be, 3. So this answer is going to be what? Pull the 2 out and you're left with a 3 in the radical. Square root of 13 stays. Square root of 14 stays. Square root of 15 stays. And you're like, how is she coming up with these? Think of all the factors of 14. 1 and 14 and 2 and 7. None of those are perfect squares. 3 and 5, none of those. So we know 16 goes here. So I want you to look at what we have. We have the ones that we know are perfect squares. And then we have a couple others that aren't. But here's a big hint. 4 is going to be like something you use a lot. If it's a multiple of 4, won't it be in the side? So 24 would go here because it has a factor of 4, which is a perfect square, right? Okay? Where do you think 50 would go? What are the factors of 50? $50 would go on the not simplified part because 5 times 10, what good is that going to do you? Nothing. But what about the square root of 2 times the square root of 25? Does that work? And what is the square root of 25? 5. So pull it out. You just set it free, but that's got to stay. Got it? Okay. So here's what I would like you to try to do. I'm going to give you this packet. You're only going to work through those first